Find the power series for this differential equation, part B. Open parentheses, x plus 1, close parentheses, multiplied by the first derivative of y equals 3 times y. Now again, we will go back and say y of x is equal to the sum from n equals 0 to infinity of a sub n times x to the n, and y of x, or y prime of x, is equal to the sum from n equals 1 to infinity of n times a sub n times x to the exponent of n minus 1 end exponent. Now let's actually replace these function. It's a generic function because we don't know the coefficients yet. Let's replace that into our differential equation so that we have open parentheses x plus 1 close parentheses multiplied by the series from n equals 1 to infinity of n times a sub n times x to the exponent of n minus 1 end exponent. And that will be equal to 3 times the series from n equals 0 to infinity of a sub n times x to the n. Let's go ahead and multiply our coefficients in. This is actually going to become a couple of, we're going to have to expand the x plus 1 binomial term into a series. So I'm going to end up having 3 terms. This will be the sum from n equals 1 to infinity of n times a sub n times x to the n plus the series, or the sum, from n equals 0 to infinity, or actually, sorry, that's n equals 1 to infinity of n times a sub n times x to the n minus 1. And that will be equal to the sum from n equals 0 to infinity of 3a sub n times x to the n. Now let's adjust our indices so that we have all powers of x to the n. Looks like we only need to mess with the second term. So this second series will be equal to the sum from n equals 0 to infinity of open parentheses n plus 1 close parentheses a sub n plus 1 in subscript times x to the n. And we'll bring down the other 2 power series. Now at this point, we need to remove the 0th terms so that our starting values are the same. And in fact, that would be the, yes, we'll do that with the second and third power series in our equation. So this will be equal to a sub 1 plus the series n equals 1 to infinity, bracket n times a sub n plus open parentheses n plus 1 close parentheses a sub n plus 1 end subscript end bracket x to the n equals 3a sub 0 plus the sum from n equals 1 to infinity of 3 times a sub n times x to the n. Now we have 2 sides of an equation, so we want to equate coefficients here. First thing we notice is that a sub 1 equals 3a sub 0. And then also n times a sub n plus open parentheses n plus 1 close parentheses multiplied by a sub n plus 1 in subscript is equal to 3a sub 0 as long as n is greater than or equal to 1. Those coefficients will hold in that recursive relationship. Now that means that a sub n plus 1 in subscript is equal to a fraction, open parentheses, 3 minus n, close parentheses, times a sub n. That was our numerator, with a denominator of n plus 1 in the fraction. So let's start using some values of n. Since this relationship is valid for n greater than or equal to 1, let's take the value of 1. If n is equal to 1, then this means that a sub 2 is equal to 2 times a sub 1 over 2. And since a sub 1 is equal to 3a sub 0, that is equal to 3a sub 0. All right. How about a3? That would be an n value of 2. a3 is equal to a sub 2 over 3, which coincidentally is equal to a sub 0. And then let's see, a sub 4 actually is equal to 0. And because future terms depend on the previous term, all the rest of our terms will be equal to 0. So we can write y of x is equal to, actually let me put it up here, y of x is equal to a sub 0 plus 3a sub 0x plus 3a sub 0x squared plus a sub 0 x cubed. And they all have an a sub 0 term in common. And then we can also actually factor this. It's going to be a, well, sum of cubes. Well, no, that's not quite the right term. But we can factor this. And so it becomes y of x is equal to a sub 0 times open parentheses 1 plus x close parentheses cubed. It's based off of a binomial series. Well, anyways, so y of x, our general solution, is equal to a sub 0 parentheses 1 plus x close parentheses cubed. And that is the power series solution. Happens to be a finite function, finitely termed function, but it is a power series solution to that differential equation.